All right. Now we're going to be on to a pretty challenging calculus application for APC, and that's resistive forces. So we're defining a resistive force as a force that depends on velocity that serves to oppose the object's motion. Realistically, this is just types of drag, and we're going to almost exclusively do linear drag here, because if not, that would not be a very fun calculus exercise. Linear drag is bad enough. And the reason this is a challenge is because net force gives acceleration. So if the acceleration depends on velocity, if velocity changes, acceleration changes. That means acceleration isn't uniform, so we can't use kinematics. But what we do know is we'll be given a relationship between the velocity of an object and the rate of change of its velocity. So we'll have a differential equation to solve. So the general strategy will be writing a help minus hurt equation, setting that equal to ma or m dv dt, right? Because we said that if f net is equal to ma, acceleration is just the derivative of velocity. We're going to have some function that depends on velocity on the left side and the rate on the right. So we can do some manipulation here. So our strategy here is going to be do your help minus hurt equation and solve for dv dt. And then you have to separate everybody. So you want one side of your equation that only has velocity variables in it, and the other side should have just t variables in it. Or usually it'll have nothing, because usually there's no t involved. Just send all the v's over to one side. Usually this involves division, and then we integrate. So the velocity will start at some value v0 and then end at v, and time always starts from 0. And we will see that if you have linear drag, we get an exponential function that decays either to some asymptote or to 0. And then if you need anything else, just start taking derivatives and integrals. Easier said than done, though. This is quite a lot of calculus. If you haven't done differential equation separation in your AP Calc yet, you might want to just put this section off. Like, you can slot these sections in any order. This is probably one of the last things I would recommend looking at in this class due to the calculus required. It's not the power rule. So we'll look at an example here. This is the easiest case of drag, which is where an object is just slowed to a stop by a drag force. So crate is moving, and there will be a force opposing its velocity given by a drag constant times the velocity itself. And since that's the only force, the object will be slowing down and it eventually stops. So what we'd like to do is draw the forces exerted on the crate at each of the following times. At t equals 0, a little bit later, and a long time later. So we know the drill at this point. This is a crate on Earth that's not falling through the floor. So there will be a constant gravitational force at all times because it's on Earth. And there will also be a constant normal force exactly balancing that. No issues there. And now we also know that the object will be slowing down due to this drag force. So originally we're launched at a speed v0. So we are moving. So if we're moving, there's a drag force because the drag force depends on v. The bigger the v, the bigger the drag. So there will be a very large drag force exerted on this object as soon as it begins moving. So this will be our drag force. Then a little bit later, the object would have slowed down. So if the object slowed down due to the drag, that means the drag would be even lower because there's less velocity. And then a long time later, you could draw an even lower force if you want, or you could say it stops, but usually long time means infinity for me. So if it has been slowing down for an infinite amount of time, I am going to just make the executive decision here and say it is stopped. Maybe we'll use green for that. So notice here, we do have a very different acceleration that's happening. So we want to indicate whether A goes up, goes down, or remains constant. Well, the net force tells us the direction of the acceleration. So the acceleration would be large and to the left, the acceleration would be smaller and to the left, and the acceleration would be infinitesimally small or just zero. So we can see that since the net force is decreasing, the acceleration is decreasing. End of story. So the key here is that the slowing down crate results in a decreasing drag force, which results in a decreasing acceleration. Let's sketch a graph of the position, velocity, and acceleration of the crate as a function of time. Label the vertical intercept of each curve. So we have our choice of where we can begin. I think the thing we know the most about is the velocity. So we know for sure that the velocity of the crate will begin at some value, v0. Then initially it's going to slow down really quickly. So it's going to have a very large acceleration or slope. Then it will slow down less and less and less and less and less, flattening out. So we will get a exponential approaching decay function here. If I can do better than that, I'll make it decay quicker just to show. All right, now we can just do curve sketching to think about what the acceleration would be. So we have large negative, smaller negative, smaller negative, smaller negative, smaller negative approaching zero. So we do actually need to label the vertical intercept of this, which we'll deal with shortly. But we do know that the acceleration will look like this, where it's a large acceleration that flattens out. So what will that acceleration be? Well, we know acceleration is F net divided by m, or in this case, it would be the drag force divided by m. And if we go back up to our problem, it says the drag force is C times V. So initially, we have a drag force of CV0 in the negative direction, and our mass is lowercase m? No, uppercase m. So that's that. All right, what about the position? Well, the position is just going to be something whose slope is v, or we could think about it. So we do know that we start at 0. Initially, we're going to be moving fast, then we slow down, then we slow down, then we slow down, then we slow down. We're going slower, 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 slower. So that will give us a curve like this. And these all actually do have asymptotes because they will approach a value after a long time. And we're going to be interested in the one on the x because it's not 0. All right, by writing and solving an appropriate differential equation, derive an expression for the velocity of the crate as a function of time. Well, the general expression for this is just solve for dv dt, and then we do some separating. So we do know that F net is just help minus hurt. Is anything helping my crate move? No, nothing. What's hurting my crate? The drag force. So my net force is just negative CV. Not CV0, because the V could be anything. Now, what is F net? F net is MA. Actually, I think we'll just use Newton's second law. Acceleration is F net divided by m. So the acceleration would be negative CV divided by m. So this is not a differential equation yet. It's just an equation. So we have to relate v and a using derivatives. Well, of course, a is the derivative of velocity. So I can write my differential equation as dv dt equals negative c over m times v. Still not what we want. This is just the intermediate step. So this is quite involved when we have these. All right, so our general strategy for solving a diff EQ is once we get dv dt by itself, send all v's to the other side, usually by division. It would be great if we can divide just the v, but if we have to carry extra things over because they can't be separated, it's fine. Here we can just divide both sides by v, right? I can just divide by v, divide by v. That works. So I can do dv dt times 1 over v is equal to negative c over m. And separate means get the dt to the other side also, so we just send that dt over via multiplication. So dv over v would be equal to negative c over m times dt. So we have separated, so this is called separation, because all the v's live on one side and all of the not v's live on the other. Then we integrate. So this is separate. Then we need to integrate. So dv over v equals negative c over m dt. So we integrate. V ranges from v0 to some value v at a later time. T ranges from 0 to t. So we separate and we integrate. Now, here's where we might sort of be outpacing your calc class. This is a special antiderivative. It does not follow the power rule, because if we're trying it, we would get v to the 0 divided by 0. So it's actually special. It turns out this antiderivative is a natural log. So 1 over x, the derivative of natural log is 1 over x. And nothing weird is happening here. So then we can evaluate. So ln of v minus ln of v0 is equal to negative c over m times t. You have become uncapitalized in these lines, apparently. Now, a log property says that we can crunch these logs via division. So natural log of v over v0 is equal to negative c over mt. And now we can exponentiate both sides, or e both sides. I like to just say e both sides. If e and ln touch each other, they cancel. So I get v over v0 equals e to the negative c over mt, or v equals v0 e to the negative c over m times t. And I'm sure that's exactly what we guessed the answer to be. I say that jokingly, but as we get more familiar with this, it is very possible that you can just solve these FEQs by inspection. And I'd actually suggest you do that when possible. So let's make sure this makes sense. So this should make sense because we have an exponential decay. So that looks like this. So the velocity does decay, and its initial value is v0. So what would be the acceleration of the crate as a function of time? Well, the acceleration of the crate as a function of time would just be the derivative of the position function. Or sorry, the derivative of the velocity function, rather. So all we have to do there, remember the derivative of an exponential is itself, and then we got to do the chain rule. So this would just be v0 e to the negative c over m times t times the derivative of the exponent, which is negative c over m. So we'd get negative cv0 over m e to the negative c over m times t. What about the position? Well, we can find the displacement of the crate just by integrating the velocity function. So we can find how far the crate has gone. So again, delta is just the difference. So this would mean our final position minus our starting position, which is 0 in this case, so goodbye to that term, is equal to, well, if the derivative of this is the original function times negative c over m, we just got to divide to get the antiderivative. This would be negative m over c v0 e to the negative c over m times t evaluated from 0 to t. This means x would be equal to negative mv0 over c times e to the negative c over mt minus 1. Or just grouping it to make it positive, this would be mv0 over c times the quantity 1 minus e to the negative c over m times t. Now, this has a really nice property. This function, I call this exponential approach. This is always a function that starts from 0 and approaches a maximum value. So this function always looks like the behavior we expected on the other page. It's this asymptote idea. And we can check that because if I plug in 0 to this, I get the value in front. Sorry, if I plug in 0 to this, I get 1 out of this term. And if I plug in infinity to this, then this term goes away. So determine the position of the crate after a long time. This means take the limit as t approaches infinity. Which would just be mv0 over c times the quantity 1 minus e to the negative infinity. And we've taken that as a fact that that's just 0. That's mv0 over c. And how is this position visualized on x of t? Well, position after a long time means what are we approaching after a long time? So this would be the horizontal asymptote. So this position right here would be this green line, mv0 over c. All right, would you believe that that was just the first problem? All right, now we're going to do what I call the driven case of this, where there is a force helping you, and then there's a drag force building up fighting you. So this would be a case where you drop an object, and it reaches, and there is a drag force. So the object will speed up as it falls, but also as it falls, it'll pick up speed, so the drag force increases. So what this means is that eventually you'll be moving so fast that the drag force balances the mg force driving you, and it'll experience constant speed. So that's the breakdown of our free fall model, where we don't believe in air resistance. Because really, after a long time, or not a long time, depending on what you drop, that drag force will be so large that it balances mg. So there's a constant final speed, right? Terminal means end. So a is 0, and f net is 0 after a long, long time. All right, so we have a ball that's tossed upwards, except now there is air resistance, and there is a force proportional to velocity. So first, have a ball. It's on Earth. Definitely gravitational force involved. Then we have to deal with the drag force. So if we're traveling up, means the ball is moving up. So this means that there would be a drag force down. And then if we're traveling down, this would mean that there is a drag force opposing that, so the drag force would be up. And it is still going to accelerate or slow down. So I know the drag force isn't going to be equal to mg right here. And then when it's traveling down, or sorry, this is down. And then when it's traveling downwards, there would be a opposing just that way. It could be equal to mg after sufficiently long, who knows. So here, our acceleration would be really down. And here, our acceleration would be slightly less down. So after being released, after delta t up, we have reached max height. And after time delta t down, from there, we have hit the ground. So we want to compare these. Now, this is obviously the same in free fall, because everything is nice and symmetric in free fall. But is it when we have drag? And we are asked to justify referencing the forces in part A. So notice that as the ball travels up, it is being slowed down by gravity, and slowed down by drag. So you have a double slowdown happening. So the brakes are fully pressed when you're traveling up. But when you're traveling down, yes, gravity is trying to speed you up and take you to the ground, but drag is fighting gravity. So the braking acceleration is much larger than the driving acceleration, which means it's not going to take you very long to go up. It's going to take you a lot longer to go down. What did I say here? Same vertical distance. Drag forces add when rising, creating a large acceleration, and they subtract when traveling downwards, creating a small acceleration. So, since you have a lower acceleration in scenario 2, that process takes longer. So, now we're going to do it explicitly, where we have an air resistance force, BV, that opposes the motion. We're dropping an object from the top of a large cliff. So let's do our differential equation. So when we're dropping the object, we know that there will be a gravitational force, mg, and there will be a resistive drag force equal to bv for this problem. So anytime we have to derive the differential equation, we need to do Newton's second law. So the net force would be, we should always start from help minus hurt, so it's clear. What's helping the ball move? Mg. What's hurting the ball? Bv. Now we can solve this for acceleration. So this would yield, acceleration is going to be F over m, which is also dv dt. So this means dv dt would be mg over m, which is g, minus bv over m, which would be b over m, times v. So that is our differential equation. Derive an expression for the velocity of the ball as a function of time. Well, we have our diff eq, so now it's time to separate and integrate. This is going to get ugly. All right. Well, we have our starting point is dv dt equals g minus b over m times v. We say that we want to separate first. So separate. I need to get the v to the other side attached to the dv. So I can't do that unless if I divide everybody. So dv, because you can only have the v and the dv attached via multiplication when you take an integral, right? So v is g minus b over m times v. That would be equal to dt. So we have separated. Now we integrate. And in this case, we're dropping it from rest, so we have no initial velocity, and we end with some velocity v. And now we got to take the antiderivative of this thing. So we just have to do the reverse chain rule. So we know that if it's a 1 over x object, the antiderivative will be ln of the stuff. But remember that if you ever have anything multiplied by your variable, any constants, we have to do division after we take an antiderivative. Again, I would just say, just look this up at this point. Like, this is not the skill we're assessing at this point. So divide by negative b over m, which makes negative m over b. So we evaluate that from 0 to v, and then that would just be equal to t. So now we got to start simplifying. So I'll multiply this over to both sides. So I'd get ln of subtraction turns into division. So I get ln of the upper limit divided by the bottom limit after multiplying both sides by this object. Then we look clear to e both sides. So I'd get g minus b over mv divided by g is equal to e to the negative b over m times t, or 1 minus b over mg times v is equal to e to the negative b over m times t. So this would mean e to the b over t minus 1 is equal to negative b over mg times v. Or we can multiply and we would get v equals mg over b times the quantity 1 minus e to the negative b over m times t. And if we were paying attention, we would know that this is the approach function. So the v is going to start at 0 and it's going to approach a maximum value given by this, which we will know as the terminal velocity. That is disgusting. This is my least favorite thing in all of Physics C, is solving the Diffie-Qs. Now, eventually, you can actually just memorize these. On the actual AP test, we give you points for this and this. Like, we don't care about all the algebra garbage. So if you just memorize what the solution looks like, you're good. After you set it up, you must be able to set it up and separate, though. All right, let's find terminal speed of the ball using force balancing and the velocity function. So first of all, force balancing is pretty easy because when v is equal to v terminal, there is no net force because the velocity is not changing anymore. So we just set our up forces equal to our down forces. So the up force is bv, and our down force is mg. So our terminal speed is just mg over b. And this should make sense because if your mass is larger, that is a larger force that needs to be supplied, right? That's why mg is on top. So it's a larger speed required. And also makes sense that as this drag constant gets bigger, the terminal speed is smaller because you need a lower speed for the same force. All right, what about the velocity function? So we said that the velocity function looked like this. So at terminal speed means speed after a long time. So v of infinity is just going to be mg over b times the quantity 1 minus e to the negative infinity. Goodbye, right? You were 0. So what a surprise, we get mg over b. It is always just true that when you have the 1 minus e to the negative function, this is the terminal value. That's why we write this parent function. All right, let's sketch some graphs, label all intercepts and asymptotes. Well, the first one that we nailed is that the velocity function is the exponential approach, right? Because I start from 0 and approach a max value. Acceleration, notice it is getting shallower, 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 positive, approaching 0, because we said down is positive. And we can think about what this intercept should be. So initially, when I drop the object, it is falling, but there is no velocity, so there's no opposition. So free fall, no opposition. This would just be g in free fall before quickly decaying. And then the position function, we can think about what this should look like. So I'm going to start at 0. Then we speed up and eventually become linear. So this is going to be hard to show. So we need basically a function whose slope is equal to this. So, after a long time, we're going to approach like a linear function. So I would say, let's see. So I need large positive slope, and it eventually flattens out. Keeps speeding up and up and up and up and up, though. Something like this. I'll correct this. It should definitely be like eventually linear-ish. So it should be trending towards linear, but the slope is increasing. It's just increasing by less and less and less and less. So a slope that gets steeper and steeper as time goes on, but by a lower amount. Yeah, I can't draw that. I'm bad. I'll fix this when I upload it. All right, last question. It's the coffee filter lab. All right, so common lab is assuming we have linear drag with coffee filters. So drag equals constant times V. And we want to find this like drag constant. So suppose that we're just doing this lab where we have a motion detector so we can get the velocity as a function of time. We can plot the speed of the coffee filter. And the students notice that basically as soon as you drop the coffee filter, their speed is constant. So first of all, let's find the terminal speed of n coffee filters. So we said terminal speed is going to occur when we have force balancing between the drag force and Fg. So the drag force has increased enough that it totally balances mg. Drag force would be CV. And then it says the terminal speed of n coffee filters. So each coffee filter has mass m. So every n coffee filter would contribute a mass m to the cause. So this means that our terminal speed of a set of coffee filters would be nmg divided by c. All right, what could be measured by students to determine C, and how could we reduce uncertainty? Well, notice that to determine C, we need literally everything else, and this means collecting multiple trials. So we're going to use the motion detector to find the speed terminal. So after a long time or when it levels out, what's the speed of a stack of n coffee filters? We're just going to do it over and over again, different values of n, get a lot of data points. So measure the terminal speed of the stack of n filters, collect data for a lot of n. So how could we use a best fit linearization to solve for c in this case? Well, the terminal velocity is nmg over c. The things that we collected were terminal velocity and n. So this means that terminal velocity would be equal to mg divided by c times n. Again, it's always good practice just to put your variable at the very end of these lab expressions. You can figure out what's going in the box with it. So a linearization you could do is terminal velocity goes in the box. Capital N goes in the other box. And then mg over c would be your slope. So you'd graph terminal velocity versus n coffee filters. Slope of the best fit line is equal to mg over c. So mg divided by the slope should be your c. But you could just stop here when we have a slope relationship. We didn't say solve for c. We said figure out a relationship between c and the slope of the graph. All right, now this is a very physics C thing. You can have linearization with exponentials. So what if instead of using velocity, students use the acceleration? And we'll just say that this is the formula that spawns. This is the formula that spawns out of the differential equation that gives you the acceleration of the coffee filters as a function of time using a single coffee filter. So the students have plotted the acceleration as a function of time. So we do have that, right? We have A and we have T. So we do know that this is our equation that we're going to use because of the mass of the coffee filter. And I'm just telling you that whenever you have an exponential like this, a decay function only, you can log both sides and that gets you a straight line. Let's try it. A is equal to g e to the negative c over mt. So the issue here is the e, right? So we have to log both sides. That's a lot of letters. So ln of a would be equal to, I can't do anything right now, actually. I can't cancel these because ln and g don't touch. So I have to use the product property of logs, where I break this into ln of g and ln of e to the negative c over m t. And now I can cancel this term, e and ln at least. So I'd get ln of a would be equal to, this term rewritten would be negative c over m times t plus ln of g. And this is actually linear because ln of a, that's nonlinear. Okay, go in the box. T, that's fine. T can go in the box. And ln of g, that's actually fine because that's just a number. G is just a number. So log of a number is a number. So this is actually your y-intercept. And then c over m, negative c over m is your slope. This gets you kind of a funky linearization. You will have no units on ln of a. Technically, we divide by a unitless constant, but whatever. So this is your log linearization. If this is the first time you're seeing it, kind of interesting, but generally this is the technique. You log it, you product split it, and you get a straight line. So of course we did the mining off camera. This is weird because it actually has a negative slope and a y-intercept. So this is what I got when I graphed ln of a versus t. And this is what Desmos got. So now we can solve not only for the drag constant c, but also g. So if you're asked to solve for two things from a linearization, that means you're probably getting a slope and a y-intercept and have to do stuff for each. So we said that according to our model, the slope of our best fit line symbolically should be equal to negative c over m, meaning c is going to be negative m times the slope. So we would get negative, the mass of a single coffee filter was 0.001 kilograms. We can check that. Yeah, 0.001. Yes, 2 zeros, not 3. And then times the slope, which is pretty close to negative 20. And the units of our slope would be nothings divided by seconds. So we would get, is that 0.02? Yep. So the drag constant c would be 0.02 kilograms per second. And then to conclude, we'll actually get g. So g is related to the y-intercept. So according to our equation, y-intercept is actually natural log of g. So the y-intercept is actually the ln of g. So we can e both sides to get g is e to the y-intercept. So that's odd looking. So e to the 2.28. And we know this will have the same units as the acceleration. So e to the 2.28, I'm getting 9.78. And look at that, that's definitely very close to 9.8. All right, wow. Yeah, you can see why I'm saying this is among the hardest mechanics sections. I do think there's one topic that's harder than this, but this is about as hard as it gets with all the differential equations and the log linearizing. So this is a rough one.